Oh, yes, and that's why they're filling the space. It's more like bees around a hive. You don't walk in there. That'd be a bad place to go. But the bees are just filling that space all over. Well, the electrons are moving so fast that they fill up the space too. Okay, so this model has some advantages, but disadvantages. If you want to talk about it in simple terms, this one is pretty nice to use. Okay, so we have protons where? In the nucleus. Who else is in there? Neutrons, always?
No, as long as they exist, they're there.
Yes.
If you got neutrons, they're there. How about, would they not be there?
Hydrogen atom.
Hydrogen atom is, once again, your simplest one. How many protons? One. Who else is there? One electron out here in the cloud or in the orbits. And that's it, right? So what's in the center?
At that time, just one proton.
One proton, that's right. And what's its charge? It's positive, +1. If you don't have any neutrons and you lost your electron, what would you be?
A proton.
A proton. A naked proton, nothing else. Have you ever thought about that?
No.
No, but now you will, okay? Because that is true. What's a proton? Well, it's a hydrogen atom without its electron and has no neutrons. So, do all hydrogen atoms have neutrons?
No.
Obviously not. Do some of them?
Yes.
Yes. Some, a small number, have one, each one has one neutron. Okay? But there's an even tinier number that have two. So a hydrogen atom could have no neutrons, that's what most of them are like. Or it could have one neutron, that's what a small number are. Or there could be two neutrons, that's what a really small number are. If you took a basket out with tweezers and went to find all the hydrogen atoms you could find, first of all, it's ridiculous because you won't be able to handle them. But if you did, you'd come back from that hunt, that scavenger hunt, and you'd have all these atoms of hydrogen, and most all of them would be no neutrons. Because that's the most common isotope of hydrogen. So what's the most common isotope? One proton, one electron. You say, surely it's got a name. Doesn't it have a name? Yes, it has a name. And we're going right now to the top of page 28 to see what we're talking about. Oh, wrong one. Top of page 28. Bless you. So here we have how many protons? One here, one there, one there. So who does this have to be? Hydrogen. If you look at the number of protons, it tells you who it is. I don't care what you say. It's got its identity showing because the number of protons is very specific for the element. So anybody that has one proton has to be hydrogen. Okay? Anybody that has two protons has to be helium. Okay? So, do we have a name for that number of protons?
Mm-hmm.
Yep, it's called atomic number. Write that down. The atomic number is the number of protons in an atom. Atomic number. Atomic number, number of protons in an atom, which gives you its identity. If you know the atomic number, then you know who it is.
But you said the atomic number is the
Number of protons. I did not say number of electrons. If it's a neutral atom, it should have equal numbers of protons and electrons. But it's possible to take away an electron or to add one. So that's not a good way to define it. The best way is protons. You want to mess with the protons? Then you're in the wrong school because that's a nuclear reaction. And we don't do that here. Okay?
that'd be a really fun class.
That would be the last time we did it. Yes. So the normal chemistry that you do, you're messing with the electrons, not the protons so much. But if a proton lost, if a hydrogen, this one lost its electron, it is a proton. Okay? And we do talk about proton buildup later on in other times in this course or AP2. AP2 mostly. Okay, so you got it. Number of protons, atomic number tells you what? Tells you the identity of the atom. Yeah. Okay. What about neutrons? Oh, this is the only one that might not have one. This is the only one that doesn't have one. Hydrogen without a neutron is called, they didn't give it to you, which I wish they had. Protium. Protium. Write that down. Let me look it up for you too, the spelling. Here it is. Protium. A stable isotope of hydrogen. In fact, most hydrogens are protium.
It's the most abundant element in the universe.
Probably, too. Hydrogen, the Big Bang and all.
So is it a collection of hydrogen atoms that make it?
Protium is one kind of hydrogen atom, but it's the most common by far. And it has one proton, just like all hydrogens have, but it has no neutrons. That makes it protium. So it's a hydrogen without any neutrons.
But I was asking in terms of like acid, so is that just a bunch of protons?
Okay, yeah, an acid is a proton donor.
Okay.
So it would donate these types of things. It's very interesting, actually, to kind of contemplate, because if you had a protium and lost the electron, it's nothing but a proton, because it didn't have anything else. And that's the kind of thing that an acid donates. Acids are proton donors. Who's the receiver for the proton? The base. Yeah. All right, enough of that. So what if you had what if you had one neutron? Now it's deuterium. One neutron, one proton, deuterium. Okay. What's the charge on a neutron?
0.
0. The charge on the proton? Positive charge. Okay, electron? Negative. 1. Okay. Tritium, you've got 2 neutrons. And what are you actually changing? If you're not changing the charge, what are you changing? The weight, the mass. That's right. So, what would you want to make with deuterium?
Helium.
That would require some stuff we don't do here. How about 2 of these and an oxygen? What would that be?
Water.
What kind of water?
Heavy water.
Heavy water, and they use that in experiments too. Okay? Heavy because the red one weighs the same as the yellow one, they have the same mass, so you have double the mass of the hydrogen here, and you mix it with oxygen, you got heavy water. That's a side view that we don't need to keep going on, but that's what's kind of interesting too. Do you know what they do? They put heavy water in certain labs or in certain living organisms, and then they can trace where it goes. Because they can trace that. They can pick up that it's heavy water, not just regular water. So they can follow the process through and see where the stuff's going.
So organisms don't really dissolve heavy water properly?
They can have heavy water, it's just there's not much of it because you don't have as many deuteriums. But in the lab, you can make heavy water, then you can inject it into something if you're wanting to know where the carbohydrates go or stuff like that. You can follow through with that.
Yeah, but that's my question. That would mean that that living organisms can really work with heavy water.
They can
So
work
it would
with
stay
it.
the same. So
They
you
can
just
work
trace it.
with it, but you can also notice it's there and therefore trace it. Trace what it's with, where it is. I don't do this, but,
Okay.
scientists can use that as a tracer.
That's how they measure what metabolism is doing.
Right, things like that. Okay, let's go on. So, tell me, what's an isotope? Or what are isotopes?
Atoms that have different numbers of nuclei.
Atoms of the same element with different numbers of neutrons. Who's the only atom that has no neutrons?
Protein.
Protium. This is protium, they didn't label it. This is deuterium, and this is tritium. Here we have mixtures. How about that? Can you mix sugar and water? What do you get? Sugar water. Is that a solution? Yes, as long as you don't put too much sugar in there, it'll dissolve. What do you call the sugar?
Solute.
Solute. What do you call what's dissolved in? Solvent. Okay. Is it all evenly spread out through here, the sugar? Yes. What would you call that kind of liquid? It's homogeneous. Homogeneous, because the sugar is spread all the way through. It's a solution. Solutions are homogeneous, the same throughout. If the particles in there, they're sugars, but there's so little in there, you don't even notice it. And you taste it, but you don't notice it. Here you've got a colloid. Colloid, the particles are a little bigger. And an example of colloid is jello or gel, Vaseline. Those are colloids. The particles are a little bigger. So if you have a little bigger particles and you shine a light through, the light scatters when it hits them. But in a solution, the light does not scatter when you shine it through. Yes?
So does that mean in our thyroids and the vesicles there, when it says that everything's hanging out in like the colloid chambers, that
Yeah.
there's like a little jelly
So
chamber?
it's a little more jelly-like, yeah. And remember our osmotic oncotic pressure? They talk about it as a colloidal type setup there too. The suspension here, so if you had a bucket out at the beach and you got some sand in it, swirl it around, and you had some little parts of shells in there, and swirl it, set it down, come back in 2 hours, what's it like?
Sediment on the bottom.
It settles down, okay? The sugar is not gonna do that. The sugar is so well mixed in here, it's not gonna do that. The colloid's not gonna do that either, but the suspension will precipitate it out. Here's a suspension for you. Take some blood, what do you do to it?
Separate the plasma.
How? Spin it in a centrifuge, and look what you get. You get the red blood cells all going down to the bottom, and you have the plasma up above. Okay, so it was a suspension. It settled out. But this liquid, what's in there? What's in the liquid?
Water.
Water for sure. What else? Is that where your blood sugar is? Glucose? Is that where your sodium ions are? Yeah. Potassium ions, yeah. Calcium ions, yeah. So that's a solution. So you can have a solution and a suspension kind of together. Okay? And even blood is sticky too, right? If you cut yourself, just a little one, and the blood's there, you notice that stickiness when you run your finger into it. Well, that's because there's some colloidal characteristic there too. All right, what are these supposed to represent? Different mixtures, okay? The smallest particles are solution, the largest are suspension. Can we take a carbohydrate like glucose? What's in it? Carbon, what else? Hydrogen and oxygen. What's a hydrate? hydrogen and oxygen, it's a water situation. And carbon. So carbohydrates have carbons, they have hydrogens, they have oxygens. Your hexoses are sugars, aren't they? Ose. How many carbons? Six. If you had 5 carbons, it would be pentose. Okay, you got the idea there. Can you tell the weight of each carbon? Yeah. Can you multiply it times 6? Yeah. That gives you the amount of the atomic weight that comes from the carbon. You can do it with hydrogens too, 12, but they don't weigh as much. So you get 12 here, and the oxygens times 6, you get almost 16 there, and it's times, almost 16, and you're multiplying by 6, come up with 95. Add this all up, and that's your total atomic weight, okay? So you can figure out the relative quantities here of these, okay? Now, are atoms and molecules so big that you can work with them easily? No, they're teeny. If you lost an atom, who would know? They're so small. So you're not gonna pick them out and put them in a pile and say there are 6 of them there. That's just not gonna work, okay? So our regular way of working with this doesn't work so well, okay? So what we do is, we take a certain quantity of like the sugar, and we weigh it and say, okay, this quantity of sugar weighs this amount, okay? And there are loads and loads and loads of molecules there of sugar, okay? How many donuts in a dozen? 12. How many in a baker's dozen? 13. My last class never heard of that.
I've never heard of that.
You haven't? Well, so there are people out there that haven't heard of it, but not after today.
Yes.
What's the
Okay.
meaning of that?
I think the baker was being nice and put an extra one in, which I approve. I think that's nice, okay? So, then, what's a ream of paper? You need a ream of paper, a printing paper, how much are you getting?
Is that 10,000?
No, that's way too much. 500. 500. They're even starting to do half reams. If you check it out, maybe you've seen that. Okay. But anyway, it's supposed to be 500. Well, when you're working with a lot of stuff, you can break it into dozens and stuff like that. So somebody wanted to make up a quantity, and it's huge, but it's small. And his name was Avogadro. And it's his number in 1 mole. He said, I'm gonna work with moles. Well, we said, what's in a mole? He said, oh, only 6.02 times 10 to the 23rd. We go, oh my word, that's a huge number. Yeah, but we're talking about molecules that are so small it doesn't matter. If you were talking about planets, where are you gonna put that many planets, you know? So he got this idea to call it a mole. They named it Avogadro's number, 6.02 times 10 to the 23rd. You should know what that is. And so he could figure out how many sugar molecules were in this quantity because he knew how many should be there. So it's Avogadro's number. So I'm just mentioning it. In chemistry, they're not gonna pull out so many sugar molecules. They have to work with the larger quantities and say, we know in a liter of this stuff or in a kilogram of this stuff, there would be this many, and they can figure out what you are working with and how many you should get. I just want to mention it. I'm not going into detail. Take chemistry. You can find out about it there. Okay? Whose number? Avogadro's. And it's 6.02 times 10 to the 23rd. They've got a product out there. Maybe you've run into it. Avocado's number. They have avocado guacamole type thing. And they used his number to just advertise it. Avocado's number.